In the previous video, we have covered the simulation of an equilibrium reaction and the equilibrium reactor, where we use the example of nitrogen plus hydrogen giving to the ammonia, the Haber process. In this, we use the equilibrium constant as 1.2 bar square. So now, next we will see what are the results. So when you see the results, you will realize the conversion of nitrogen is only 88.54 percentage. Thus, this is a good conversion as a chemical reaction, chemical engineer. If you see, this is not a good conversion. It might be a good, but what we want when we are producing some products, the conversion should be close to 100%. Why? Because if it is not close to 100%, then the next task is to separate the products from the reactants and resupply the product for conversion, which is just increasing the inefficiency of your process. And using the separation method will increase the costing of your production because separation comes with a cost. So what we need to do, we need to optimize the conversion in the reactor. So the objective of this simulation will be optimize the conversion of reactor, find out the value of equilibrium constant at which this will occur, which is more or less the same thing, and learn optimization in DWSIM, how we optimize the things in DWSIM. And we will use, we are not gonna again simulate this whole thing. You can watch the previous video for the same. In this video, what we are gonna do, we will simulate and figure out the optimum value of the equilibrium constant. So let's start. Now go to the simulation. Here what you will do, I saved it as a equilibrium 1 DWC in the recent files. You just open it. Otherwise, the next thing you can do, file, open file, and choose the file wherever you have saved these. Now, after this, what I will do, you can see, I will just write in all the properties table. And we will just focus on this. Okay. So our objective is to optimize the conversion. So I will go to the flow sheet analysis. I will do the sensitivity study. In this case, I will go for a new case. And in the new case, my objective is my independent variable. What is the independent variable? It is independent of the anything. It is what? It is changing. It is the change we want to introduce in the process, which will result in another change. Let's say temperature is independent, but the reaction rate is dependent. Similarly, pressure is independent, and the gases, the state of the products like liquid vapor or gases is the dependent. So here my independent variable will be reaction property, and that is the equilibrium constant value. What is the lower limit? I know 1.2. I get the good result. I will go to till 2.5, and I want to see it in the 10th step so that this is really a good analysis and I can see if it is a linear or it is some. I just want to capture the nature of the graph also. So I will just increase the number of points. Now I will go to the dependent variable. Here I have only one dependent variable that is there in the equilibrium reactor, and it is conversion of nitrogen. Its unit will automatically should appear. Right? They are not appearing. I don't know. Yeah. Now units are appear. Now I will go to results. I will say start sensitivity analysis. Okay. Now you can see I get some more different things. Chart. I will say draw the chart. Now you can see till 88 to 1.2. Here for the conversion, if you see the results table, uh, it is 88.5. At 1.4, it is directly jumped to 99.714. For me, the study will be now what I will do. I have seen like it is going close to 100 at around uh, 1.4, 1.5. Okay. So what I will gonna do now, I will see if there is a sudden jump from 1.3 to 1.4. I go there. I will put here 1.3 to 1.4 and I want to go in 10 steps. So you can see this is what I want. I will switch to other sensitivity analysis. Now you will see, okay. Now I will draw the chart. Now you can see still there is a jump. From in the jump you can see from results you can see it is at 1.31 to 1. It is 1.34 to 1.35. So for anything, what I can say 1.35 is it should be my reaction constant value because at this only I am getting the conversion close to 100%. Why not 1.4? Why not 1.5 or why not other value? Because I am getting very incremental change in the conversion. But to increase that thing to 1.4 or 1.5, I might require to change a drastical change in the temperature. I might require a drastical change in the temperature that will come out of the dependence of K on the temperature. So for that, what we will do, we will take it at 1.3 this case and let's check what will happen at 1.3. So I will go to the thermodynamics reactions, ammonia production. I will make it as a 1. Okay, let me cancel everything. First I will save it here. Save all. Yes. Yes. Now now I go to the flow sheet. Here you can see it is showing same value. Settings, ammonia production, it is 1.4. Now I will make it as a 1.3. Okay. Now I will solve this. I think I might have put the wrong value. So it is 1.34. Okay. Let me solve it. Because it is incremental increase now. So okay. Yeah. So directly go to the 1.4 to check whether our analysis is correct or not. Result to re-verify the analysis results. And so yeah, our analysis is correct. At 1.4 we are getting the conversion is 99.74. So this is how now our next step will be to figure out at which reaction conditions 99.74 we can achieve, how to increase the K value. So that is the temperature dependent. Just increasing the temperature will increase the K value of the reaction. Let's say somehow I figure it out. K is at 120 to make this case realistic. I will plug 120 and you can see all the factors that is affecting it here. And now it is just reduced in this conversion. This is because of I increase the temperature, which in result which will in result increases the partial pressures of the other partial pressures of the reactant and the products, and the dynamics will be played by their stoichiometric coefficient. So there is a little bit reduction in the conversion. So just I need to optimize the temperature. I should always optimize for the temperature at which I should link the temperature and the reaction constant. So this is also there available. You can see here we can introduce K as a function of temperature. Then I will just increase the temperature in my sensitivity analysis and I will get at which temperature I will get the highest production. That will be the ideal case scenario, but this data is not available with us right now. So we are not simulating in that way. We are simulating another way. We figure out at which K value at the same temperature and pressure we are getting the conversion, highest conversion. So I hope you get the intent of this video. It is just about to let you know familiar with the optimization in the DWSIM. So that's okay with this. We will meet in another video where we are going to separate the reactant and the product.